Sure, sure.
Hello, everyone. Today we have Jun-Yan Zhu as our speaker. Jun-Yan Zhu is a postdoctoral researcher at MIT. He got his PhD from UC Berkeley in 2017 and his undergrad degree from Tsinghua University. His research interests are in computer vision, graphics, and machine learning. He has received many awards, including a Facebook Fellowship, ACM SIGGRAPH Outstanding Dissertation Award, and the David J. Sacrison Memorial Prize for Outstanding Doctoral Research from UC Berkeley. He has served as a technical paper committee member at SIGGRAPH Asia 2018 and the guest editor of International Journal of Computer Vision. Let's welcome our speaker.
Thanks for a nice introduction. Could you help me in the back seat? I see. Oh, sure, yeah. So, could you help me now? Cool, yes. Yeah, thanks for coming to my talk. I would like to talk about how to learn to generate images. So in 2012, the field of visual recognition experienced a revolution. The arrival of deep learning. Within a year, the old handcraft pipeline was replaced by the new end-to-end trained deep nets. Since then, we witnessed an enormous jump in recognition performance on the standard benchmarks, and many real-world applications become possible, from object detection to human understanding to autonomous driving. So around the same time, many people in computer vision and computer graphics were asking if deep learning can also help visual synthesis, which is try to generate images with a network. Maybe we can take a network, simply flip it, and use it instead of the traditional graphics pipeline, which involves modeling, texturing, lighting, etc. However, this did not work at all. So it turns out that using deep nets to produce high-res images, high-res data such as images, is extremely difficult. So why it's difficult? So for a very long time, the deep nets can only generate digits using CycleGAN for a variety of applications like photo enhancement. You can train a model on the bad images versus good images, and it can enhance the photo for you. You can train a model, here is the images with haze, and image without haze, it can dehaze the image for you. And also, it's not only work on images, it also works on like other kind of representation, like you have the motion data, and it can stylize the motion for you. So the first row is the input motion, and the second is the different style. You can see the hand is slightly different, and so you can represent each motion with the joints, 2D joints. So it's like 20 joints, and each one has two-dimensional. And you can train LSTM as your generator, not a CN, but LSTM. But you can apply the same CycleGAN laws on top of that. And here is the video. So this is input, and you can train a model. There are subtle differences. There are roughly similar motion, but there are some characteristics of each motion. So it will also not only work on images, it also works on these motions and also work on the geometry data, like 3D data. So actually, there are lots of applications beyond computer vision, like medical imaging, convert your voice to like Obama's voice, for example. And like robotics, like and NLP. I always want to have a CycleGAN. I write some text, and it can improve it, and I just submit to the conference. So I just show you one example. Here is we try to translate. I think researchers try to translate input MRI images to a CT scan, and it looks quite realistic to a ground truth CT scan. But I think my favorite results are not from the researchers, but from Twitter. So this is the one I recently saw on Twitter. And as a cat lover, so my dream is to transform every dog picture into a cat one. But if you love dogs, don't worry, we have the cat-to-dog transformation just for you. And here another one. So it's a good excuse to search on Twitter. just to check out some research. So if you are a gamer, you probably heard about these two popular battle royale games, Fortnite and PUBG. So what if you love the gameplay of one game but want the graphics of the other? And CycleGAN can actually do it for you, and can change the texture and rendering and some buttons and icons, and it's pretty cool. But the only issue here is the resolution. Pix2Pix and CycleGAN can only produce up to 512p results, so it's not ready for the serious gaming applications. So to address this issue, we introduced Pix2Pix HD for better resolution and higher quality. I will briefly go through the message. So here is the high-res input layout with roads, trees, buildings. So would it be wonderful if we can also generate high-res image out of it? Unfortunately, the Pix2Pix does not work very well. You can see all the artifacts, and because again, the game is a Minimax two-player game. So it's very for high-dimensional data. It's very hard to optimize this game. So to address this challenge, together with researchers from NVIDIA, we proposed Pix2Pix HD, a divide and conquer strategy inspired by the image pyramid. So it's a very classic idea in computer graphics and vision. So the idea is we first generate low-res output, and we further upsample the low-res output and refine it using a second stage network. So essentially we decompose a hard problem into two easier ones. So we know how to generate low-res output, as Pix has done, and we know, we just upsample 2 by 2 or by 4 times. It's easier than generating a high-res image directly. So by given the above cost-to-fun procedure, Pix2Pix HD can produce a nearly photorealistic images at 2000 by 1000 resolution at real time. And here are some results. And we also have an interface which allow you to manipulate the images. You can insert a car at a particular location. You can add some trees just by painting some trees jokes. In addition to the straight images, Pix2Pix HD can also produce high-res faces given rough sketches. So here are the face images generated by this model. Again, you can also change the attributes of the faces. So I think so far in summary, we have improved the control quality resolution of images generation methods based on GANs and deep learning. And I think hopefully these tools can help everyday users to tell their own visual stories, like describing a cat you would like to adopt, imagining a street you would like to visit. But there are still a very long way to go, and there are many, many open problems. So I will describe a few next steps, some ongoing projects I was doing at MIT. So the step here is we try to, instead of learning to generate 2D images, we try to actually learning to recreate this entire visual world. And there's a few things we need to do. First, we go from a 2D image, but actually in practice, we want the cars can move, and we try to generate a video rather than a 2D image. And also, given the same particular moment and this particular image, we should be able to change the camera viewpoint. And so we can see different viewpoints of the same object and same car. And eventually, I will not mention here, but eventually we'll try to generate the 4D and the 5D light field function, which is you sample different camera viewpoints and at any location in the world. So I will talk about these two projects, which will try to not only generate an image, but also generate a video. And so a car can move around. So the goal is to generate a video given these input semantic label maps. And so the challenge here is if you just apply the Pix2Pix HD frame by frame, there are lots of flickering artifacts, as you see in the video, because there are no temporal consistency across the different frames. So our idea is we have some method based on the object motion is the idea is we not only we take the semantic maps and the past images. So the generate conditional on the previous frames, conditional on the input, and we generate the flow maps and also the intermediate another image. The flow map is basically so each pixel in this flow map is basically which pixels will the pixel should move in the next frame. So we are using this flow map. We are reusing the images we have generated. We don't need to generate again. We based on the previous frame, we generate the next frame, and we can warp the flow map, and we combine this together. And we do it again and again, but we take the previous frame as input. So when we generate the next frame, we take the previous generated frame as input. So we know what's going on in the previous frames. And also we have a multi-scale discriminators, which is each discriminator look at different scales of images, and also not only the spatial resolution but also the temporal resolution. It look at this resolution, but you can subsample the videos, and so you can look at every single frame, but you can look at the resolution at every 2 frames, every 4 frames, like this one. So this video discriminator will tell you if the motion is realistic or not. You probably heard about this progressive training. Is basically we can, as we did before, we first train a very small image and very low frame rate, and then we upsample again. The idea is we first train a low resolution output, and we add the input, high-res input, and as we did before, and generate high-res output. But we also do it for the temporary domain. We first generate a very short video, and we generate more video, and generate more video, and more videos. And we do it actually in an alternative way. So we first generate a very small image, and we generate a little bit longer video, and we upsample the resolution, and a little bit longer. Yeah. So each stage is a relatively easy problem compared to you want to generate the final result directly. So here are some results we get. It's still not perfect, but you will see it's much better than the previous method. So here is the input, and this is the frame by frame. This is a different method. This is our results. We also have some. You can also generate not from semantic label map to Street View. You can also generate the pose from pose. This is a pose tracking from another person. You can generate a new transfer the motion from one person to the other. So we extract this pose map from different actors, and you can synthesize a different person. Yeah. So that's one idea. We can generate moving objects. Another idea is can we generate a moving camera? Can we not only generate a single image, but generating different viewpoints of it? So for that, you probably have heard all these GANs. There are GAN papers every month or every day, but people are still working on generating 2D images. So here are some samples from 2D GANs, but we are living in a 3D world. So in this work, this is a work to be appeared in NIPS. So we not only generate 2D images, we also generate 3D voxels. We sample a viewpoint project into 2.5D representation, like the normal and the depth, and we generate the final image. So this will allow us to change the viewpoint of a particular car. We can change the shape given the same viewpoint, same texture. We can given the same viewpoint, same shape, change the texture. So this allows us to manipulate and generate images in a 3D fashion. And here's how we train the model. I just briefly discussed the idea. Is first we have a model to generate 3D voxels. So we train this model. So we have a bunch of thousands of like real voxels, and we try to generate generative voxels so that it looks like these real voxels. And then we project, given a particular viewpoint, we project into a particular into a particular like depth and mask. Note that this projection module is actually it's a little bit hard to implement. Actually, we try to make sure everything is differentiable. So later you can get the gradients from 2.5D to 3D. And later we based on this 2.5D sketch, we sample a texture code and we add a texture. And so the training signal from two sources. One here is we try to say the generate 3D voxel should look like a real voxel. And here we want to say the generate image should look like a real image. So we have real image as training data, we have real voxel as training data. And here are some comparison to the 2D baselines. So here are different GAN methods, recent GAN methods. And here are our results. So we can not only generate a 2D image, but we also generate voxel. You can rotate. And here are some results on chairs. Yeah. Yeah, I think that concludes my talk. So I think we are doing a very great job in generating 2D images, but they are actually generating videos and high resolution 3D objects. Eventually, we can generate a virtual reality experience, which you can generate some data, which you can actually have a VR device and you can watch. We are still very far from there. But that's thank you my collaborators and advisors, and thank you for your attention. Yeah.
The model doesn't want to change the background much. So I was wondering if there's any way to apply a trained GAN model to like high-level visual recognition tasks like recognition, detection.
Yeah. I think your question is if there is a way to apply a GAN model and extract some semantic knowledge from the GAN model and apply it to computer vision tasks. So I haven't shown here, but we have done some work here. You can actually when you translate a horse to zebra, you can one thing we did is you can actually first ask the model to predict a mask, and then you only translate in the pixels within the mask. And it turns out that mask network is a very good segmentation model of horse. That's one thing we try, and we also have another work just submitted to the iClear this year. Yes, we can actually it's a paper should not mention the paper, but we can locate each unit. We can analyze each unit in the GANs, and we found some units can detect the trees. If you generate an image of outdoor church images, it can detect trees, detect sky, detect walls, and we can actually use these units for segmentation tasks. Yeah, we can talk offline. Yeah, cool.
You mentioned that in the CycleGAN, you do not need space, for
Yeah.
example, to train this.
Yeah.
Convert from horses to zebras.
Yeah.
And then you convert back zebras to horse and you close the cycle
Yeah.
and try to minimize the loss. Isn't there inherent loss of information when you convert horse to zebra? Because there can be many horses correct for that zebra.
Yeah. I think the question is there any information lost in this conversion? I think yes, and also, although the loss was not minimized to zero, so there are some residual, like it's not optimized to zero. But there are also some follow-up work from Montreal. They try to introduce latent vector like random code to the CycleGAN. So you not only predict the generate a zebra, but also generate a code which encodes the original horse, and you can use that code to come back. So it kind of encodes some style information in the code space. So I can share you with the paper later after the talk. Yeah. Cool. Yeah. Could you speak louder? Yeah. Sorry.
My question is, in practice, if I apply CycleGAN to generate some image, but the image I'm not satisfied with, what should I do? Should I get more training or should I adjust something to make that? I know it's not,
Oh yeah. Yeah. I think your question is how to make it's a very general. It's how to make CycleGAN work better. If I know, I will maybe publish another paper. But yeah, I think more training data will help, and more some data pre-processing like alignment. For example, if you crop the horse and the zebra, it works much better. I mean, but it's an easier problem. If you can crop the horse and the zebra, you don't care about background. You crop the cat and dog, it works much better. And although there are some new follow-up papers like trying to invent some like different architectures and there are different new loss functions. Yeah, I will encourage you to check some recent work. Yeah. Cool. Thanks. Yeah.
So in doing all this research, what have you learned in terms of like, is the discriminator learning something that we can generalize or amortize across different tasks? Are they learning sort of actual perceptual loss functions over images, the connection between sort of conmat and perceptual features that makes sense?
Yeah. Yeah, I think Suranshu's question is what the discriminator has learned through this training process. I feel in the past we have used the discriminator. So people are using this VGG network to extract some feature and calculate some perceptual distance. But we have actually replaced the VGG network with the discriminator, and it still works. Indeed, people are using some random weight network, and it still works. So yeah, I think. But we don't find discriminator to capture lots of information. So by the end of the day, if your GAN is perfect, the discriminator should produce garbage, right? So everything is 0.5. But I think people have often used an encoder. They say, so you first have a generator and you train an encoder to invert its generator, and the encoder will work better for other tasks compared to the discriminator. Yeah. Yeah, I think most people they will use both the perceptual loss and the GAN loss. I also saw some hybrid. Is you can first extract features with the VGG network and do a GAN loss on the feature space. This also shows work better compared to a GAN or VGG. So basically you fix the first 5 layers and allow the GAN to do the another 2 layers. But I think the idea of GAN is that so it works for like other tasks like the medical imaging and other kind of tasks which you don't have a very good pre-trained model. And also it's kind of ultimately so actually you actually can do GAN without ImageNet and all the AlexNet stuff actually. So yeah, but I guess it's more like interesting to have a fully unsupervised method. But if you working on a particular domain, like you working on faces, you can actually use some FaceNet, which is trained on faces, and will work better compared to a GAN. But yeah, cool. Thanks. Yeah. Thanks.